Now we're on to Chapter 15, Other Equilibrium Systems. Previously, we saw about ionic compounds that do not dissolve in water. They're called insoluble, right? They do, however, dissociate into ions when placed in water. Compounds that do dissolve by dissociating with their ions are called soluble. In reality, even insoluble compounds dissolve to some extent. They are called sparingly soluble. Then equilibrium exists between the precipitate and its ions. So silver chloride, for example, is a sparingly soluble ionic solid. When it's added to water, it dissolves slightly and produces a mixture consisting of a very dilute silver ion and a chloride ion in equilibrium with the undissolved silver chloride. So this is strontium chromate. Strontium chromate also is slightly soluble, and it gives strontium ion plus a chromate ion. The KSP is called a solubility product constant. At equilibrium, the solution is saturated with the dissolved ions to the extent that they are dissolved. And so you can form that, from that you can form the same type of KSP type of constant as you did with the other ones. The concentration of the strontium ion times the concentration of the chromate ion equals 3.6 times 10 to the minus fifth at 25 degrees centigrade. Like all equilibrium constants, the solubility constant has a fixed value at a given temperature. The product of the two ion concentrations at equilibrium must have this value regardless of the direction from which the equilibrium is approached. One way to establish a solubility equilibrium is to add a sparingly soluble solid to both water and then stir it up. Eventually the solution, even though it may take quite a bit of time, becomes saturated with the ions. In other words, the compound reaches the total solubility, that's the maximum. In a saturated solution, an equilibrium exists between those that are dissolved in that solution and those that remain undissolved as a solid. And it's, again, like every other equilibrium, it's a dynamic situation. You can calculate the solubility of a compound from its KSP value. The solubility will have the units of moles per liter, M, and it's called the molar solubility. Instead of calculating the solubility from the KSP, it's also possible to calculate the KSP from a compound from its solubility. There are many sources listing the solubility of the sparingly soluble compounds. As a matter of fact, this is very important when you are looking at different pharmaceutical products, because many of them have very low solubility unless they have some sort of a salt associated with them that helps bring them more into solution. And then by doing so, making them more bioavailable. So depending upon the source, these solubility values are expressed in many different units. But what we're going to do here is always make certain that we have the molar solubility units in terms of the moles when converting and working with the equations of the KSP. Now we're talking about the common ion effect. If you have barium sulfate, it will, as a solid, in the solution you will have some barium ions and some sulfate ions. Now, when you add some other type of barium to that material, or if you add some sulfate there, for example, if you put it in a 0.1 molar sodium sulfate solution, what happens then is a result of the Le Chatelier's principle. Because you have a common ion of the sulfate there, the presence of that will drive the equilibrium back towards the left-hand side of that equation. So common ions reduce solubility. So how would you expect the solubility of barium sulfate in pure water to compare with its solubility in 0.10 molar sodium chloride? Well, the thing is, it's a trick question. You have to have a common ion in order to have the common ion effect. So putting it into a solution like sodium chloride instead of a sodium sulfate solution is not going to have any effect whatsoever on it. In this one right here, you've got copper bromide forming copper and bromide, copper ions and bromide ions in solution. The initial concentration of the copper ion and the bromide ion is 0. Once it it's in solution for a while, or once it's in the solution for a while, eventually you will reach the equilibrium concentration. So you can see from this equation here, what I did is I wrote out how you can predict that. You have the KSP, which is, in this example, it's given in your book there, is 6.3 times 10 to the minus 9th. Since you have concentrations of copper ion and the bromide ion, that would be essentially the one times the other, or x squared, is going to equal that, that should be 6.63, not 68. I mistyped that. So it should be 68 times 10 to the minus 10th. I did it to the minus 10th power because I'm then going to take the square root of both sides. On the left side, that gives me a straight x, and on the right side, because it now is 7.9 times 10 to the minus 5th. I always make certain that I have an even number over here so that it makes it a lot easier for the power of 10 here. And then I just make the adjustment appropriately on this right here when I go through these. Likewise, if you've got calcium hydroxide as a solid, the ions in solution are going to be the calcium ion, and there you are also going to have the hydroxide ions. So here what you have is something a little bit different. Keeps wanting to shift on me. Here you're going to have the situation where you have x times 2x squared equaling that 1.3 times 10 to the minus 6 moles. And that's because KSB is going to equal the concentration of the calcium ion, which is straight x. Then you've got 2x for the concentration of the hydroxide ion, but it has to be raised to the squared power. And so what you'd have to do then is you'd have 4x cubed. And 4x cubed equaling to 1.3 times 10 to the minus 6th. What you would do is you would then take the cube root of that, and that, when you do that, you end up with the 6.8 times 10 to the minus 2. And again, because it's minus 6, you're dividing that by 3, and the 1.3 works out to be just exactly that number right there. So, now, recall equilibrium can be approached from either direction. With the strontium chromate, we had the strontium ion and the chromate ion. So you can start with just the reactant, that is the solid, or you can start with the products. If you have the reactants, you add in a solid compound to water. If you're starting with the products, you're adding the ions to the water. And if you mix two solutions, you have strontium nitrate and potassium chromate, what you end up with then is something that you will have both of them, the chromate ions on them, strontium chromate, and for the KSP, you'll have at any point in time before it reaches equilibrium, you'll also have the Q value there. The KSP values can be used to predict whether the precipitate will form when ions from the solution are added to the water. And you use the Q coefficient then in the same form as KSP, just noting that you are using the exact concentrations at any given point in time since it has not yet reached equilibrium. So the precipitate formation occurs, the relative magnitude of Q versus KSP will indicate whether or not a precipitate will form. If Q is much greater than KSP, the first instance there, a precipitate will form. That decreases the ion concentrations until the equilibrium is established. However, if Q is less than KSP, the solution is unsaturated. No precipitate forms, and if desired, more compound can be dissolved. When Q equals KSP, the solution is saturated just exactly at the point of precipitation. Now, you can do something called selective precipitation, and a lot of times when we are purifying a material, we utilize this technique to separate a cation by adding an anion that will form a precipitate with only one of them. The precipitate can then be removed by filtration, while the other cation remains in the filtrate. And this approach is called selective precipitation, and as I said, we've used this frequently as a method of purifying different pharmaceutical products. An example of that, a rather trivial one, is the solution of magnesium and sodium ions. Most sodium compounds are soluble in water. Magnesium can form a compound with the carbonate ion, but it's only sparingly soluble. The KSP for that is 6.8 times 10 to the minus 6th. Now, if you were to add barium ions at the same concentration, and the carbonate ions are slowly added, and that is much less soluble than magnesium carbonate. The difference in the solubility can be used to separate the cations if carbonate ions are added very carefully. Which carbonate complex will precipitate first? Well, you can't always just compare the KSP values to answer the question. You actually have to do the experiment. So both ions will be sorry, that was just a duplicate. Okay, anticoagulants can be added to blood that will combine with the calcium ions in the blood serum and prevent the blood from clotting. That's a very useful medical application for this technology, for this chemical principle. Here we have cadmium sulfate, and and this is example 1513. In this particular one, what you're looking at is the common ion effect. Here what you're doing is you're putting the cadmium sulfate into a cadmium bromide solution. The KSP, the CDS, equals 1.0 times 10 to the minus 28th. A very, very low number. Because X is so much less than 0.01, what you can do is you can just use the, in the upper portion of this equation up here, right here, you can ignore this X right here. So essentially what you're doing is you're multiplying this concentration by the X concentration, so that what is going to happen is you will just divide this right here by the 0.01, and you'll end up with X equal to 1.0 times 10 to the minus 26th. Okay, that's the common ion effect and other special applications for those. We also have another type of acid. Okay, the one that we have talked about in the prior chapter, the Bronsted-Lowry model, is the one that is most commonly thought of, and that involves the proton transfer. But remember way back when we talked about the different models that we had for individual atoms, and we had the Lewis model. The Lewis model of an atom is one in which the electrons that are in the outermost layer are included as dots around that. And this is very appropriate for the Lewis acids and bases, because instead of looking at it in terms of a proton, we looked at an acid in terms of something that accepts a pair of electrons. And Lewis base then is something that donates a pair of electrons. So a Lewis acid-base reaction produces a product with a coordinated covalent bond. And for those times when we don't have a water solution, or when we have some rather other type of materials that don't involve proton transfer, we have a way of thinking about them in terms of how these